Okay, Bismillah Rahman Rahim. This is lecture number 3 of the course Irrigation Engineering. In today's lecture, we will discuss about the crop water requirements and its measurement. Water requirements of crops. The term water requirements of crops means the total quantity and the way in which a crop requires water from the time it is sown to the time it is harvested. So what we mean by the water requirements of crops, it means the total quantity and the way in which a crop requires water from the time it is sown to the time it is harvested. This is known as water requirements of crops. Different crops will have different water requirements, and the same crop may have different water requirements at different places of the same country, depending upon the variations in climate, type of soil, methods of cultivation, and useful rains, etc. So different crops, they require different amount of water for their growth, and the same crop may have different water requirements at different places of the same country, depending upon the variations in climate, type of soil, methods of cultivation, and useful rains that fall over the crops during the growth period. So different crops will require different amount of water, but the same crop may require different amount of water at different locations of the same country, depending upon the climate, the type of soil, methods of cultivation. Irrigation requirements of certain crops. So in this table you can see that we have the kharif crops, the summer crops. So for example, we have maize. Its period of growth is June to September, October. The average water depth that is required, that is 45 centimeter. This is the average water depth that is required to grow the maize. Now irrigation requirements, 4 or 5 waterings, sensitive to drought. If we have less quantity of water is available, then this crop is very sensitive to that. And on the other side, if floods occur, again it will cause damage to maize. Responsible to fertilizers, average quantity of seed required kg per hectare, that is 15, and average quantity of yield obtained, that is kg per hectare, 3000. So this is a general information regarding the maize. For example, we can consider cotton. So it is period of growth is May, June to November, January. The average water depth required, that is 25 to 40 centimeter. 3 or 4 irrigations are required. Damage up to the extent of 50% may be caused by flooding, rains, etc. And average quantity of yield obtained, that is 500 kg per hectare. Similarly, you can see that we have this till here. This is an ancient crop that is used to obtain the oil. This is the period of growth and generally does not require much water. You can see here, not mentioned. Generally not irrigated, but better to irrigate once. And the average quantity of seed required, kilogram per hectare 1.25, and average quantity of yield obtained 350 kg per hectare. Next we consider some rabi crops. These are winter crops. So we have wheat ordinary, that is the period of growth, that is October to March, April. Average water depth required, that is 37.5 centimeter. 3 to 4 watering of 7 to 10 centimeter depth. The seeding, average quantity of seed required, that is 80 to 100 kilogram per hectare, and the average quantity of yield obtained, that is 1500 kg per hectare. For example, we consider potatoes. So the period of growth, that is September, October to February. The average water depth required, so 60 to 90 centimeter. Usually irrigated, sown in high hills up to early April. Second crop in plains is sometimes taken in February, April. The seed that is required, kilogram per hectare 15,000, and the crop yield, that is 35,000 kg per hectare. Similarly, you can see that we have sugar cane here. So February, March to December, March, you can see that sugar cane is almost grown for the entire year, and the water depth that is required, average 90 centimeter. 5 to 6 waterings of 10 centimeter or more required. The seeding, that is 500 kg per hectare, and the crop yield 25,000 to 30,000 kilogram per hectare. So this is some general information. The irrigation requirements of certain crops to get some idea. Next we discuss the crop period or base period. Some basic concepts. The time period that elapses from the instant of its sowing to the instant of its harvesting is called the crop period. So what is the crop period? It is the time period that elapses from the instant of growing a crop to the instant of its harvesting. That time period is known as the crop period. The time between the first watering of a crop at the time of its sowing to its last watering before harvesting, it is called the base period. So base period, it is the time that elapses between the first watering of a crop at the time of its sowing to its last watering before harvesting. This is known as base period. So you can see that there is a slight difference between the crop period. It is the time period that elapses from the instant of sowing a crop to the instant of harvesting. That is crop period. Whereas the time between the first watering of a crop at the time of its sowing to the last watering before harvesting is called the base period. So it means that the crop period is slightly more than the base period, but for all practical purposes, they are taken as one and the same thing and generally expressed in B days. So B days, we will denote the crop period, and the base period is practically considered as the same, and it is denoted by B days. Next, we discuss delta of a crop. Each crop requires a certain amount of water after a certain fixed interval of time throughout its period of growth. So each crop requires certain amount of water after a certain fixed interval of time throughout its period of growth. Just like we saw in this table here, you can see that maize, the average water depth required, that is 45 centimeter. And then it has to be provided the irrigation requirements, the artificial supply of water for the growth of maize, so 4 to 5 waterings. So each crop requires a certain amount of water after a certain fixed interval of time throughout its period of growth. The depth of water required every time generally varies from 5 to 10 centimeter depending upon the type of crop, climate, and soil. So we have different crops, they require different amount of water. So that is why the depth of water required every time generally varies from 5 to 10 centimeter depending upon the type of crop, the climate of that area, and the soil conditions. The time interval between two consecutive watering is called the frequency of irrigation, and it is also known as the rotation period. So the interval, the time interval between two consecutive waterings, this is known as frequency of irrigation. It is also known as rotation period. This total depth of water in centimeter required by a crop to come to maturity is called its delta. This is known as delta of a crop. So it is the total depth of water in centimeter required by a crop to come to maturity is called its delta. It means that one crop, it requires, let's say we have this wheat here, it requires 37.5 centimeter of water on average. So this is the delta for the wheat. This is what we mean by delta. The total depth of water in centimeter required by a crop to come to maturity is called its delta. For example, if rice requires about 10 centimeter depth of water at an average interval of about 10 days, and the crop period for rice is 120 days, find out the delta for rice. Water is required at an interval of 10 days for a period of 120 days. Therefore, number of required waterings, that will be 120 by 10, 12 waterings will be required. Therefore, total depth of water required, that will be equal to number of waterings multiplied by depth of each watering. So that is 12 multiplied by 10, 120 centimeter. Hence delta for rice, that is 120 centimeter. This is the total depth of water that is required by the rice to come to maturity. Average approximate values of delta for certain important crops. For sugarcane, delta on field is 120 centimeter or 48 inches. For rice, it is again 120 centimeter or 48 inches. Garden fruits, 60 centimeter. This is the delta on field. For cotton, 50 centimeter or 22 inches. For vegetables, delta on field, that is 45 centimeter or 18 inches. For wheat, it is 40 centimeter or 16 inches. Maize, 25 centimeter or 10 inches, and other crops. So this is the delta, the total depth of water required for these crops to come to maturity. During the growth period, this is the total depth of water required for their full growth. Next, we discuss some important units. So we discuss the acre foot. You can see here that we have this 66 by 660. So this is the area. 1 acre has this much square feet. 1 acre, that is equal to 43,560 square feet. So 66 multiplied by 660 feet. So this is equal to 43,560 square feet. So 1 acre is equal to this much square feet area. Now, if we have a water over this area to a depth of 1 foot, so this become acre foot. This is the unit of volume. So you can see that 1 acre foot, that is equal to 43,560 cubic feet. This is the unit of volume. So in the previous lecture, we discussed this unit in detail when we discussed the water budget of Pakistan. So million acre feet, million is 10 power 6, and acre feet, that is the volume unit. So 1 acre foot, that is equal to 43,560 cubic feet. So we have 1 acre, and if we have the depth of water over this 1 acre, so this is known as the volume, that will be 1 acre foot. Similarly, we have 1 hectare, that is equal to 10 power 4 square meter. 1 hectare, this is equal to 10 power 4 square meter. And then 1 acre, so that is equal to 0.4047 hectare. This is how we can convert from hectare to acre and acre to hectare. Next, we discuss duty of water. So the duty of water is the relationship between the volume of water and the area of crop it matures. Duty of water is the relationship between the volume of water and the area of crop it matures. How we can define it? It may be defined as the number of hectares of land irrigated for full growth of a given crop by supply of 1 cubic meter per second of water continuously during the entire base period of that crop. So how we can define the duty of water? The number of hectares of land irrigated for full growth of a given crop by supply of unit cubic 1 cubic meter per second of water continuously during the entire base period of that crop. Clear? So this is the duty of water. We can also define in the FPS system that the number of acres of land irrigated for full growth of a given crop by supply of 1 cubic feet per second, 1 cusick of water continuously during the entire base period of that crop. So it means that for water that is flowing, unit discharge of water that is flowing for B days, that is the base period of that crop, that matures D hectares of land. So that will be the duty of water. D hectares, the number of hectares of land irrigated for full growth of a given crop by supply of unit discharge continuously for the entire base period. So that is known as duty of water. If water flowing at a rate of unit cubic meter per second runs continuously for B days and matures 200 hectares, then duty of water for that crop will be defined as 200 hectares per cubic. The duty of water that will be represented by D. So unit discharge flowing over an area for irrigation of a crop for the base period, the number of hectares of land irrigated, so that is known as the duty of water. A relationship between duty delta and base period. Let base period of the crop be B days and 1 cubic of water be applied to this crop on the field for B days. Now volume of water applied to this crop during B days, that will be equal to B multiplied by, because B is in days, so multiply by 24 hours, multiply by 60 minutes and then 60 seconds. Clear? So the idea here is that we have, for example, 1 cubic meter of water. This is the volume. So this is for 1 second. This is for 1 second. Clear? 1 cubic of water. Now the volume for B days, we want to find out that what will be the volume if it is flowing for B days. So that will be equal to 24 multiplied by 60 multiply by 60. Clear? So this is in cubic meter. This is how it comes. So this is equal to 86,400 B cubic meter. Now, by definition of duty, 1 cubic meter supplied for B days matures D hectares of land. So this quantity of water matures D hectares of land, or 10 power 4 into D square meter of area. So the total depth of water applied on this land, that will be simply equal to volume by area. So we have this volume and this much is the area. So by definition, this total depth of water is called the delta. So delta, this is equal to 8.64 B by D. This delta will be calculated in meter or multiplied by 100. So delta is equal to 864 B by D in terms of centimeter. So delta is in centimeter, B is in days, and D is the duty in hectares per cubic. So this is the relationship between the duty of water, delta of crop, and the base period of the crop. Like this, in the FPS system, we will get this relationship for the delta. Delta is equal to 1.985 B by D, or it can be approximately taken as 2 into B by D. So delta will be in feet. So delta will be in feet from this equation. B is in days and D is the duty in acres per cubic foot per second. Next, we discuss factors affecting the duty of water. The type of soil. So we have coarse grained soil. Percolation losses will be high, and this will result into low duty. When water is lost, then the area that it will irrigate, that will decrease. So it will result into low duty. Clear? Because you see here the duty definition that we defined here is that the number of hectares of land irrigated for full growth of a given crop by supply unit discharge continuously during the base period. So if there are losses, then what will happen? The number of hectares of land, that will decrease. So it will decrease the duty of water. So we have coarse grained soil, percolation losses are high, and this will result into low duty. Fine grained soil, percolation losses are less, and this will result into high duty of water. Next, we have type of crop. So let's say we have crop A that requires large quantity of water. This will result into low duty of water. And if we have crop B that requires less quantity of water, this will result into high duty of water, because water will irrigate more land area. Structure of soil. So good structure of soil is called good tilth of soil. Tilth of soil, the physical condition of the soil. So we have good structure of the soil, evaporation losses are less, and this will result into high duty. Again, we have good structure that is properly aerated because of large voids. This will result into a yield of crop increased. So you can see here we have compacted soil and we have good soil tilth. So the physical condition of the soil is good. You can see here the good structure, evaporation losses are less. It will result into high duty, and the soil that is properly aerated because of large voids, that can result into yield of crop that is increases. Next we have slope of ground. So we have steep slope, downstream portion get more water, upstream portion remain drier. So this will result into low duty of water. Properly prepared field will result into equal distribution of water, and this will result into high duty of water. Water will be able to irrigate more land area, so this will result into a high duty. Next we have climatic conditions. So temperature and wind velocity are high. This will result into more evaporation losses, and as more water is evaporated, so this will result into low duty. If we have rainfall during base period, then less irrigation requirement, and therefore it would mean high duty of water. So it means that during rainfall, the crops already get some water, so less quantity of water will be required to bring it to the maturity. So it means that less irrigation requirement. This means high duty. Method of cultivation. So not properly plowed, and method of cultivation is faulty and less efficient. So this will result into low duty of water. If land is not properly prepared for cultivation, so in that case the proper irrigation cannot be done, and this will result into low duty. Properly plowed and made quite loose, water retention capacity increase, number of watering that will reduce, and this would result into high duty of water. So that's why you can see that land preparation during the sowing of the crop and then supplying the water to the crop, this is very important. System of irrigation. Non-perennial. Perennial means that the water is continuously flowing. So non-perennial means that water is not continuously flowing. Only during flood season the water is available. Wasteful use of water that can result into low duty. When we have perennial system where water is available in adequate quantity throughout the base period. So water application throughout the growth period, soil remains continuously wet and less quantity of water will be then required. So this will result into high duty of water. So during the flood season, we supply more water, you can see here, than is actually required. This results into wasteful use of water and consequently the duty of water that is low. But when in perennial system, we have already the water that we can supply, so soil remains continuously wet. This will result into less quantity of water and the result would be high duty of water. Application of water, we have drip irrigation system that is the most efficient. This will result into very high duty of water. As we studied in the previous lecture that in drip irrigation system, through a network of pipes, we supply the water directly underneath the plants and crops. So this results into saving of water. This is most efficient and consequently for this application of water, the water has very high duty. For sprinkler irrigation system where we sprinkle the water over the crops, the seepage losses are reduced as compared to the flooding techniques. So this sprinkler irrigation is in the form of artificial rain and it results into high duty. It is less than the drip irrigation system, but still it results into high duty. Now the surface irrigation system, the flooding techniques where we flood the area of the crops with water, so this results into more waste of water and consequently then the duty of water that is low. So these are some of the factors which affect the duty of water. Next we discuss consumptive use or evapotranspiration. Consumptive use may be defined as the total amount of water used by the plant in transpiration, that is building of plant tissues, etc., and evaporation from adjacent soil or from plant leaves in any specified time. So this is consumptive use. This is also known as evapotranspiration. And consumptive use is the total amount of water used by the plant in transpiration, that is building of plant tissues, etc., the water that the plant use for its growth, and evaporation from adjacent soil or from plant leaves in any specified time. So what is the difference between the delta and the consumptive use? You see that the delta of the crop that we studied, that is for the whole period. That is for the whole period of the crop growth. So the total depth of water required during the entire growth period of the crop that is known as a delta. This is we define delta. Whereas the consumptive use, that is the total amount of water used by plant in transpiration and evaporation from adjacent soil or plant leaves in any specified time. This is not for the entire crop period. This is in any specific time. So this is known as consumptive use or evapotranspiration. The values of consumptive use may be different for different crops and may be different for the same crop at different times and places. So because the crops, they require different amount of water, so consequently you can see here that the values of consumptive use, it is different for different crops, and again it may be different for the same crop at different times and places depending upon the climate conditions, the soil conditions. So factors affecting consumptive use, the different factors that affect the consumptive use are the same factors on which the transpiration and the evaporation depends. For example, we have temperature. So if temperature is more will be evaporation and transpiration. Consequently, consumptive use will be more. So sunlight, for example, plants, they require building of the tissues, photosynthesis process. So if we have sunlight that is available, plants transpiration that will be more. Similarly, humidity, wind movement. So if we have more wind blowing, you can see that evaporation from the surface that will increase because the wind will take away vapors, and therefore the rate of evaporation it will increase. Similarly, we have the soil topography, the precipitation, method of irrigation, depth of water applied for irrigation. So all the factors on which the transpiration and evaporation depends, consumptive use or evapotranspiration will also depend on all those factors. Next, we defined effective rainfall. So precipitation falling during the growth period of a crop that is available to meet the evapotranspiration needs of the crop is called effective rainfall. So in agriculture, in irrigation, we define the effective rainfall is that precipitation falling during the growth period of crop that is available to meet the evapotranspiration, this consumptive use, or evapotranspiration to meet the evapotranspiration needs of the crop is called effective rainfall. So it does not include precipitation loss through deep percolation below the root zone or the water lost as surface runoff. So we have precipitation, that part of the precipitation that is used by the crops in meeting the evapotranspiration needs, that is known as effective rainfall. This effective rainfall, it does not include precipitation loss through deep percolation, that is the water infiltrates into the soil and then travels downward, that is known as percolation. A deep percolation, that this water through the percolation joins the groundwater zone of saturation, so deep percolation below the root zone, because this water, if it travels vertically downward below the root zone, then the plants will not be able to extract this water. So that's why it will not be part of the evapotranspiration needs, the water that the plant extract. And the water lost is surface runoff. You can see that in hydrology, you might have studied that we have total rainfall. We have the total rainfall and minus abstractions. Abstractions are all the losses. Abstractions. Abstractions. So total rainfall minus the losses that, for example, can be the water infiltrated evaporation and other depression storages. So this was actually the water that appears as surface runoff. So this was actually called as effective rainfall in hydrology. Clear? This was called as effective rainfall that appears as surface runoff. Effective rainfall. But you see that then there was a confusion, because in irrigation or the people in agriculture, so they say that this effective rainfall is that part of the rainfall falling during the growth period of crop that is available to meet the evapotranspiration needs of the crop, that is known as effective rainfall. So consequently, then in hydrology, what we did is that we actually then call it as excess rainfall. We now call this as excess rainfall. That is the rainfall that appears as surface runoff. And we reserve this effective rainfall as precipitation falling during the growth period of crop that is available to meet the evapotranspiration needs. Next, we define consumptive irrigation requirement. It is the amount of irrigation water required in order to meet the evapotranspiration needs of the crop during its full growth. It is the amount of irrigation water required in order to meet the evapotranspiration needs of the crop during its full growth. It is therefore consumptive use exclusive of effective rain precipitation, stored soil moisture, or the groundwater. So irrigation water that artificially we have to supply. Clear? So it is that amount of irrigation water required in order to meet the evapotranspiration needs of the crop during the full growth. That water that we have to artificially supply, that amount of water. So that is known as consumptive irrigation requirement. It is therefore consumptive use exclusive of effective precipitation, stored soil moisture, or groundwater. So consumptive irrigation requirement, so this is equal to consumptive use minus effective rainfall. Next, we have net irrigation requirement. It is the amount of irrigation water required in order to meet the evapotranspiration needs of the crop as well as other needs such as leaching of salts. Net irrigation requirement. So in addition to meet the evapotranspiration needs of the crops, we will need to supply the water for leaching of salts, removal of salts from the soil, because in the soil sometimes the salts are present. These are not beneficial. That is because of which we have salinity, harmful salts. So how to remove them? We have to provide some additional water that can dissolve these salts, and then that water can be drained, either surface drainage or subsurface drainage, to remove these salts. This is known as leaching of salts. So net irrigation requirement, it is the amount of irrigation water required in order to meet the evapotranspiration needs of the crop as well as other needs such as leaching of salts. So net irrigation requirement, it is consumptive use minus effective rainfall plus water lost in deep percolation for leaching. Another term, that is field irrigation requirement. It is the amount of water required to meet net irrigation requirements. Now net irrigation requirement, this is net irrigation requirement. Amount of irrigation water plus other needs plus water lost in deep percolation for leaching of salts. So it is the amount of water required to meet net irrigation requirements plus the water lost in percolation in the field water courses, field channels, and in the field application of water. It is given by field irrigation requirement is then equal to net irrigation requirement divided by eta A, where eta A is the water application efficiency. Next, we have gross irrigation requirement. It is the amount of water required to satisfy the field irrigation requirement. This is now the field irrigation requirement, and the water lost is conveyance losses in distributions up to the field. So in the above you can see that is the water lost in percolation, that is the seepage losses that can occur here, and in here is the water lost is conveyance losses when we convey the water in distributions up to the field. So in this case the gross irrigation requirement, that is equal to the field irrigation requirement divided by eta C, where eta C is the water conveyance efficiency. So this is how we can calculate the gross irrigation requirement. Next, we discuss the potential evapotranspiration and actual evapotranspiration. What is the difference between the two terms? So we know that evapotranspiration is the total loss of water from farmland as evaporation and from plants grown on it as transpiration. If sufficient moisture is always available to completely meet the needs of the plants, the resulting evaporation is called potential evapotranspiration. So it means that That evapotranspiration, that is evaporation plus transpiration from the plant leaves under unlimited supply of water. When there are no limitations on the supply of water, you see, if sufficient moisture is always available to completely meet the needs of the plants, under that condition, the evapotranspiration that will take place, that is known as potential evapotranspiration. The real evapotranspiration occurring in a specific situation is called the actual evapotranspiration. Whereas actually in the crops, we cannot have unlimited soil moisture or supply of water. So that is why the real evaporation or the real evapotranspiration occurring in a specific situation is called the actual evapotranspiration. Now, what is the concept of these two? So you can see here that this ETO, this is also known as the reference evapotranspiration or the potential evapotranspiration, but it's commonly called the reference because it is for a reference crop such as a grass. So we have this as the reference. You will see this terminology when you discuss evapotranspiration. So you will see that this is known as a reference evapotranspiration. A reference ET, evapotranspiration. Now this reference evapotranspiration actually we calculate by the use of equations are available, and this reference evapotranspiration we calculate. This is for a well-watered grass as a reference crop, so that's why this is known as reference evapotranspiration, and this is denoted by ETO in the literature. So because in this case this reference evapotranspiration, it is mainly a climatic parameter. You will see that when we calculate this, mostly we consider the climate data for that area to calculate this reference evapotranspiration. So in order to make it applicable to crops, clear? So that's why this ETO, the reference evapotranspiration, that is multiplied by a crop factor, that is Kc, and the crop factors that are calculated for the different crops, and these are available in the form of tables in the literature. So we multiply this reference evapotranspiration with the crop factor to get the crop evapotranspiration, so that it is reflected for that specific crop, well-watered crop, optimal agronomic conditions. Now it can happen that sometimes we have water and environmental stress due to the conditions of the soil. We can have water and environmental stress. In that case, we have to multiply this with another factor, that is for the soil, that represents the soil conditions in addition to the crop factor here. So this is how the evapotranspiration for the crop that is adjusted. But most of the time we are using this one here. We calculate this reference evapotranspiration, which will mainly depend on the climate conditions. You can see here radiation, temperature, wind speed, and humidity in the equations, and then we multiply this with the crop factor that is calculated for the different crops to get the crop evapotranspiration. So these are some basic terms. Next, we study how to estimation of this consumptive use. Consumptive use or evapotranspiration for these crops. Clear? That we studied here. Consumptive use or evapotranspiration. So how we can measure this? We have direct measurement of consumptive use. For this we have different methods available to us: tank and lessee meter method, field plot, experimental plots, soil moisture studies, integration method, inflow and outflow studies for large areas. Direct measurement of consumptive use. We can also calculate this consumptive use by use of equations that were developed. So those equations include the Blaney-Kreidel equation, Hargreaves class A pen evaporation, and we have the Penman's equation. So we discuss these methods in detail briefly. First, we have direct measurement of consumptive use by tank and lessee meters. So how we measure it? Tanks are containers set flush with the ground level, having area of 10 meter square. This is the area, and 3 meter deep. The depth is 3 meter. Larger the size of the tank, greater is the resemblance to root development. This will reflect more natural conditions. Consumptive use is determined by measuring the quantity of water required to maintain constant moisture conditions within the tank for satisfactory proper growth. So in this case, what we do is that the consumptive use, that is the water required by the plants to meet its evapotranspiration needs, by measuring the quantity of water required to maintain constant moisture conditions within the tank for satisfactory proper growth. This is how we are assessing the consumptive use. In lessee meters, the bottom is pervious. Consumptive use is the difference of water applied and that draining through pervious bottom and collected in a pan. So in lessee meters, the bottom is pervious, so the water is supplied to the crops that are grown in lessee meters, which are containers like water tanks. This one here, the tanks that is used to grow the crops. So in lessee meter, the bottom is pervious, so water is supplied to the crop that is grown in lessee meter. The crop will use the water for its evapotranspiration needs, and remaining water that will be draining through the pervious bottom, and that is collected in a pan. So the consumptive use is the difference of water applied and that water which is drained from the lessee meter at the bottom. So the difference of the two, the water applied and the water collected at the bottom, that is how consumptive use is calculated. You can see here that in tank and lessee meters, this is how the crops are grown and the water is supplied here. In case of the tank, so that is consumptive use is determined by measuring the quantity of water required to maintain constant moisture conditions within the tank for satisfactory growth of that crop. This is how we can estimate the consumptive use. And in case of lessimeters, then the water will be collected from the bottom, it will be pervious, and the water applied and the water that is drained, the difference will give us the consumptive use. So these lessimeters, these are very expensive to install. Here we are trying to replicate the natural conditions of the growth of the crops by supplying the water. So this is actually very expensive to install. Plus these lessimeters, these are very sensitive instruments. So the water that is applied and then the water that drains has to be collected in a pan so that we can effectively measure the difference of water applied and the water drained at the bottom in order to calculate the consumptive use. The second method, that is field experimental plots. So in this method, irrigation water is applied to the selected field experimental plots in such a way, you see the area that will be divided into different experimental plots in such a way that there is neither runoff nor deep percolation. Yield obtained from different fields are plotted against the total water used, and as basis for arriving at the consumptive use, those yields are selected which appear to be most profitable. So the area is divided into different experimental plots. Irrigation water is supplied in such a way that there is neither runoff nor deep percolation. Yield obtained from different plot fields are plotted against the total water used, and as basis for consumptive use, those yields are selected which appear to be most profitable. It is seen from observations that for every type of crop, the yield increases rapidly with an increase of water used to a certain point and then decrease with further increase in water. At the break in the curve, the amount of water used is considered as the consumptive use. What we mean here, you see that if I can draw the graph here, so we have the water depth, that is the water that we apply to the crops. So we have the water depth, and we have the yield, crop yield. So what happens is that when we supply the water, the crop yield also increase, and when we continue to supply the water, then after certain condition, the crop yield will decrease. So you can see here for that water where we have maximum yield, here you can see that we have maximum yield. At this point here, so this depth of water that is required, that will be the optimum depth of water. Optimum depth. So this is what it says. It is seen from observations that for every type of crop, the yield increases rapidly with an increase of water use to certain point. You can see here up to this point here, and then decrease with further increase in water. So at the break in the curve, you see after this, the curve moves in the downward direction. The amount of water used is considered as the consumptive use.